Hello students, we are at the last lecture of module 2, and what we have seen in the second half of module 2 is how to get pipelining working, right? And we have come across a lot of concepts which would help us to handle the structural data and control hazards, right? Those were all concepts that are the building blocks of almost all the modern processors, right? With all those in mind, let's try to look at the performance aspect. Specifically, how much will pipelining be able to improve the performance of our hardware? Right, that's what this lecture is about, and this is the last lecture, like I mentioned. So, a quick recap of the non-pipelined implementations that we saw in the first half of this module. We had two possible designs, which is single cycle design and multi-cycle design. And if we assume that all the tasks are equal, typically the execution time of single cycle design and multi-cycle design is same. We do not get any extra benefit with multi-cycle design. Saying that, you would have already realized that multi-cycle design is one of the stepping stones for pipelining, right? We can't directly, it's from single cycle jumping to the pipeline version is a little difficult. So you can assume that the multi-cycle design was the intermediate step. Now let's look at the non-pipeline and pipeline implementations and try to see how much uh, in terms of performance would pipelining be efficient, right? So in a typical non-pipeline fashion, we will fetch instruction I1, we will decode it, execute it, memory access stage would be there, or step would be there, and following that we have the write back step, right? So all these five steps together would comprise of instruction execution of I1, right? Only when I1 completes its write back stage, we would go and fetch I2. Again, I2 goes through the fetch, decode, execute, memory access, and write back steps or stages, and only when it completes write back, that's when we are going to fetch I3 and start working with it, right? The major advantage of the non-pipeline version is we need not worry about the dependency among instructions, right? So there is no notion of hazards and all that. We are going to handle one instruction at a time. But what is the major downside is it's going to take a long time. So in this example, I've considered the multi-cycle design here. The CPI is 5, and so if you want to execute 100 instructions, for example, it would take 500 cycles. Now let's look at the time when we consider pipeline implementation. So I1 will be fetched and it will go to the decode stage in second cycle. At that point, we will fetch I2. Then in the third cycle, I1 will move to execute stage, I2 would move to decode stage, and I3 would move to fetch stage. So on and so forth. And by the end of fifth cycle, just like the non-pipeline version, I1 would complete, right? And I2 would complete by the end of sixth cycle. I3 would complete by the end of seventh cycle. So we are effectively able to complete 3 instructions in 7 cycles. Now, if you want to do the same thing for 100 instructions, for example, the first instruction would take 5 cycles, remaining 99 instructions take 1 cycle each. So overall, it is 5 plus 99 equals to 104. Now, if you consider a program with millions of instructions, that would be the typical size anyways. So you can neglect these the first instruction's overall time. In general, we can say that each an instruction would complete in one cycle when we look at the pipeline implementation. And so the ideal pipeline CPI would be 1, and the non-pipeline CPI was 5. So we can say that the pipelining speedup would be something like this: the execution time of unpipelined version upon execution time of pipeline version. Now we'll using the basic performance equation, if we expand the execution time, it would be instruction count times CPI of unpipelined version times the clock cycle time of unpipelined version upon the instruction count CPI of pipeline times clock cycle time of unpipelined version, right? So if we, for simplicity, assume that there were no overheads with pipelining, meaning that the pipelining is ideal pipeline, then the speed up of ideal pipeline would be simply CPI of unpipelined upon CPI of pipeline. So instruction counts of both of them will be same, and because they are assuming no overheads, the clock cycle time of unpipelined and pipeline would be same. So the ideal pipeline speedup we would expect is equal to the number of pipeline stages. So in the previous example, the ideal speedup would be 5, but we already saw that it's not the case, right? We have a lot of practical issues that we need to consider when we are looking at a pipeline implementation. A small note that the number of pipeline stages are also referred to as depth of the pipeline. Okay, so do not get confused with the terms depth of the pipeline and number of the pipeline stages. Both are same. So with all the practical implementations of pipelining included, let's see what the performance would be. The first issue is if the stages are not equal, what happens? Then the clock cycle time of unpipelined and pipelined will be different, isn't it? So what would be the clock cycle time of pipelining implementation is, or pipeline implementation is, the latency of the slowest stage. That's what we would have done with the multi-stage multi-cycle implementation also. So in this case, if we want to compare the performance of non-pipelined and pipeline version, we would typically do it with the single cycle implementation itself. That would give us a more realistic estimate of how much performance improvement would be there. Now, if we introduce the latency of the pipeline registers or interstage buffers, then the clock cycle time of pipelined implementation will be greater than clock cycle time of unpipelined implementation or non-pipelined implementation. So again, because of this, we will not be able to reach the ideal pipeline speedup. The third implementation issue is hazards, right? And to handle them, these are some equations. I'll explain, they are quite intuitive. So the CPI of pipeline implementation is ideal CPI, which is 1, plus the number of stalls per instruction due to the hazards. So this is number of stalls per instruction. Do remember that. So the CPI pipeline is 1 plus number of stalls per instruction. Now if we look at the speed up of the pipeline implementation, it would be the pipeline depth upon 1 plus the number of stalls per instruction. Now in the ideal pipeline case, this number of stalls per instruction are 0. So the speed up is equal to the pipeline depth, right? And here there is one other assumption, that the clock cycle time did not change. But if that changes, then here the equation would be pipeline depth times clock time of unpipelined implementation, and in the denominator you would see clock time of pipeline implementation. Okay, now let's look at some of the examples to understand the formulas a little better. The first example is consider a non-pipeline processor with a clock rate of 2.4 gigahertz and average cycles per instruction of 4. Now the same processor is upgraded to a pipelined processor with 5 stages, but due to the internal pipeline delay, you can say this might be the impact of the pipeline registers. For example, the clock speed is reduced to 2 gigahertz. It means that it has dropped from 2.5 to 2 gigahertz. Now, if we assume that there are no stalls in the pipeline, what is the possible speed up that can be achieved with the new processor? So we use the basic performance equations here, and we would get the speed up, which is CPI of unpipelined non-pipelined processor, which is 4 times the clock time, which is 1 upon 2.5 gigahertz, upon the CPI of the pipelined implementation is 1 because there are no stalls, times 1 upon 2 gigahertz. So it's not half gigahertz, it's 1 divided by 2 gigahertz, means it would be half times 10 power 9. Okay, 10 power minus 9. So the speed up effectively is 3.2. It means that the pipeline version of the same processor is able to give us 3.2 times the speed up. Now let's look at another example. Consider a 5-stage pipeline and assume that in the application that we are running, 30% of the instructions are load instructions. Half of the time, instruction following a load instruction depends on the result of load. If hazard causes a single cycle delay, how much faster is the ideal pipeline? So the question here is, we have the pipeline already and it has some practical issues, and if we assume what would be the speed up when we compare with ideal pipeline, right? Assuming that 30% of the instructions are loads and half of them have a producer consumer relationship with the next instruction, and because of this data hazard there is a delay or stall of 1 cycle. So let's look at how the numbers would look like. The instruction mix is 30% of loads and remaining 70% are something else like ALU or control or even store instructions. The pipeline delay due to the data hazard as given in the question is 1 cycle. Now, how frequently would this hazard occur is half of the time when the load instruction is there. So it would be 50% of 30% loads that the application has. Now the CPI of this practical pipeline is ideal CPI plus average stalls due to hazards, which is 1 plus 0.3 because 30% loads are there times 0.5 because half of these 30% loads would result in 1 cycle delay. So we can extend it as 0.5 times 1 because of 1 cycle delay. So the CPI practical CPI is 1.15, right? Now let's extend the question further. If the compiler is able to find a safe instruction and reorder the instructions and so that the data hazard will not happen all the 50% of the time, but rather in that among that 50% of the time, for 40% of the cases it is able to find a safe instruction. What happens then is the CPI would be 1 plus 0.3, which is 30% of the loads, time 50% of these 30% loads can possibly cause a hazard, but the compiler was able to handle 40% of them, so the remaining 60% would result in 1 cycle stall. So the CPI would be 1.09 here. The ideal CPI, if you remember, is 1. So in this simple pipeline, we are trying to achieve the ideal CPI, right? So if we compare the CPI of 1.15 and CPI of 1.09, which is better, is the CPI of 1.09 because we are taking relatively fewer number of cycles to execute the instructions. So our program would run faster. Now, the question was the ideal pipeline speedup. It would be the CPI real, which is 1.15 upon CPI ideal, which is 1. So the speedup that is achieved is 1.15 times. Some more scenarios. What we have seen earlier is data hazards, but what happens if there are control hazards is something similar. Let's assume that there are no data hazards. The control hazards, how do you account for them is the frequency of branches times the penalty for each branch. Okay. Now let's look at an example. Let's say we have a 5-stage pipeline and assume that in some application 25% of instructions are control instructions. Now those 25% have a mix of 7% unconditional branches or jumps and 10% of conditional branches which are taken and 8% of conditional branches which are not taken. Now with these numbers, let's try to find out what would be the CPI of the pipeline implementation. The branch penalty whenever there is a branch hazard is also given as 2 cycles. Now let's calculate the CPI of the always taken static branch predictor, always not taken static branch predictor, 1-bit dynamic predictor with accuracy of 60%, and let's say we have a 2-bit predictor, again dynamic predictor with an improved accuracy of 85%. Now if you want to look at the CPI of always taken branch predictor would be 1 plus 0.08 times 2. Now let's how do we get this is this predictor will always predict taken. So out of the 25%, 7% are jumps which are already taken and 10% are branches which are being taken. So these 17% of the time there will not be any hazard, right? But the remaining 8% we have a hazard and each hazard would result in 2 cycles of penalty. So it is 0.08 times 2. The same thing if we try to look at for not taken static branch predictor. Here the 7% of unconditional branches which will always be taken but will be predicted as not taken by our predictor will result in hazards. In the same way, the 10% conditional branches which would be taken would be resulting in hazard again. Only the 8% of branches which are not taken will be correctly predicted by this not taken branch predictor. Accordingly, the CPI is 1 plus 0.07 times 2, that will account the 7% of unconditional branches, and 0.1 times 2 which will account for 10% of conditional branches which are taken. Let's further continue and look at the 1-bit predictor with 60% accuracy. So here what happens is we have 25% of control instructions and of them the branch predictor is able to handle 60%. So the remaining 40% would result in 2 cycles delay or stalls in the pipeline or flushes in the pipeline. So the CPI would be 1 plus 0.25 because 25% of branches are there times 0.4 times 2. The same thing if you look at for 2-bit predictor, it would be 1 plus 0.25 times 0.15 because the accuracy of this 2-bit predictor is 85. So only the remaining 15% of branches would see 2 cycles delay. So this is how we would calculate the CPI. Now what if we are able to reduce this branch penalty from 2 cycles to 1 cycle? So that was the one of the first optimizations we saw with control hazards, right? Where we tried to move some logic from execute to decode stage. Because of that, what would be the CPI is in the above equations, replace 2 cycles delay with 1 cycle. So you definitely see an improvement in CPI. So with that, I will leave you to uh, do some more practice. Right, here is the theory assignment to work out the problems given in page 522 of Computer Organization and Design book by Patterson and Hennessy. Also, look at the pages A10, A14, and A25 in Computer Architecture, a Quantitative Approach, book by again Patterson and Hennessy. Right. In addition, I would like you all to go through questions 4.16, 17, 19, 21, 22, 26, and 27 and 28 in the Computer Organization and Design book that we are following. Right. This will give you a good enough practice on how we would account for hazards or any unexpected events that would happen in a pipeline, and what is the actual efficiency of a pipeline implementation. So moving on, if you want to understand what lies beyond this pipelining, right? Uh, over the past 2 weeks, we started with the ideal pipeline speed up, and then said that there are a lot of practical issues that we need to handle, and accordingly, the ideal pipeline speed up comes, drops further. So, how do we handle it better? The simple pipelining that we saw, like I mentioned in the beginning of this lecture, is very fundamental to all the processes that we have now. But there has been a tremendous progress on how processes are built now, and I will try to give you a very high level picture of how the progress has been made. They were primarily by answering few questions. The very first question that designers were asking were, can we fetch more than one instruction at a time, right? And is it possible to decode more than one instruction in a cycle, right? And the answer for that is superscalar pipeline. Now what we have is single fetch, decode, execute, memory, and write backstage, right? Now let try to replicate that 3 4 times, and together we are able to fetch, let's say, four instructions at a time. We are able to decode four instructions at a time, and possibly execute all of them at a time, so on and so forth. In that case, whatever a single pipeline was able to achieve, now the performance would be times 4 of that. The second question is how to reduce stalls, and one of the most influential ideas that was brought in is, can we reorder instructions at the runtime? What the compiler does is reordering instructions at the compile time, but that has limited scope both for the data and control hazards. But can we do the reordering at runtime? So it sounds a little tricky, but it is achievable, and we have a couple of very good implementations that are able to achieve this. What we have is called uh, dynamic scheduling of the uh, pipelines. So here the instructions will be look for all possible dependencies, and whichever instruction does not have any dependency will be allowed to proceed. So we are able to execute the instructions out of order, right? And further, this dynamic scheduling has been extended to handle the br- uh, branches also. And what we have is speculation, right? Together, both of them are called the out of order processor. The third question that the designers were asking is, can more than one program run on the same pipeline at the same time, right? So this you already know. Maybe we can possibly do some time division multiplexing among multiple programs and try to run each of them for some time, and whenever some issue comes up, we'll switch to some other program, etc. Right? That again is implemented, and we have what's called multi-threading, and it has three different variants: fine grained, coarse grained, and simultaneous multi-threading. And if you look at any of the Intel and AMD processors, you have simultaneous multi-threading enabled. So it's called SMT in short. So each core typically can handle 2 or 4 threads at a time. And again, we are trying to keep the pipeline as much busy as possible and get maximum performance from it. The fourth question is, let's say we have multiple such pipelines, which are superscalar pipelines or out of order pipelines with multi-threading on it. If we have multiple of them on available to us in a single chip, what can we do? So here we have the multi-core era. Uh, of course, this is also being driven by the power issues that we discussed at the beginning of the course, right? Sometime in 2004-5 timeline, we moved from single core to multi-core, and because we have multiple cores, we are able to handle multiple programs simultaneously and get a tremendous improvement in the performance. So these are multi-core architectures, right? So what we moved from is possible uh, parallel execution of multiple instructions, right, as part of superscalar pipelines and out of order pipelines. Then we moved to trying to execute multiple applications on the same core, and then extended it to multi cores. So what we have seen is instruction level parallelism, and as we go from question 1 to 3 and 4, we go from instruction level parallelism to application level parallelism. And further, what else was being explored is, instead of the general purpose hardware, can't we tailor make the hardware and make it super fast or super efficient in terms of energy? So that's where the notion of accelerators has come. And the most popular accelerators that you would be seeing are the GPUs and the Google TPUs, and we have IPUs, and many of the digital image processing chips that you have in your mobile phones. All of them would come under accelerators. And now imagine putting the multiple cores on the same motherboard, and along with it we are placing multiple accelerators and trying to get everything working together. That's called system on chip, right? So your mobile phone is a classic example of a complete system on a single device that works brilliantly to execute an application, right? All these have been the developments over the past 2 to 3 decades, and many of these topics would be typically discussed in the advanced architecture course. But for this course, I'm going to stop with the simple pipelining that we have discussed so far. I hope you found the pipelining concept interesting, and please do work out the program problems, and we can discuss if you have any questions with them. With that, I'll conclude this lecture. Thank you.